Alright, so today we are going to talk about Newton's second and third laws. We already talked about Newton's first law, and just a quick review. Newton's first law, or the law of inertia, is an object at rest tends to remain at rest, and an object in motion continues in motion with a constant velocity, unless the object is acted upon by a net external force. Since an object requires an external force in order to change its velocity, whether it's moving or not, it would be helpful to see what effect a force has on the motion of the object. So, what effect does the force have on the motion of the object? If we apply a force to something, how does it change the motion? In what way? Well, let's assume that we place a force on an object. Our goal is to change the velocity of the object, and this means either changing the speed or changing the direction, or both. Because remember, velocity is a vector quantity, so it has magnitude and direction. So you can change either of those and it would be a change of velocity. So our goal is to change the velocity of the object, and we can say we are also causing the object to accelerate, because remember, the definition of acceleration is a change in velocity over a change in time. So if we change the velocity in any way, we are making that object accelerate. This is the heart of Newton's second law of motion, and it relates force to acceleration. So Newton's second law is the acceleration on an object is directly proportional to the net force exerted on the object and inversely proportional to the mass of the object. And automatically the word proportional should trigger something in your brain that makes you think, oh, if I were to graph force versus mass, or force versus acceleration, I'm going to get a straight line. That should be tipping you off right now. So what does it exactly mean to have the acceleration directly proportional to the force and inversely proportional to the mass? Well, that means that the acceleration of an object over here is equal to the net force. That's what this little crazy S-looking thing is. This means net force. It's the Greek symbol sigma, which stands for sum. So we're adding everything together. So that's the net force on top, and then it's inversely proportional to the mass, so the mass is on the bottom. So if we think about this, as F increases, so as we push harder on something and apply a larger force, A does what? Will A increase or decrease? Well, both A and F are in the numerators here on either side. So as one goes up, the other goes up. As we increase the force on an object, its acceleration or its change in velocity will also increase. So that is directly proportional. However, inversely proportional is the opposite. So as the mass of an object increases, what will acceleration do? Well, think about it for a second. What's going to be easier to push, a marble or a bowling ball? A marble will be easier to make accelerate because it has less mass. So the more massive something gets, the less it will accelerate for a given force. And that's what it means to be directly proportional and inversely proportional. We tend to write Newton's second law a different way, and it's the relationship between acceleration and force. So usually when we write Newton's second law, this is what it looks like. And this is the really super important part that you need to write down somewhere in your notebook right now. The equation tells us the sum of the forces, or all of the forces added together, are equal to the mass of an object times the acceleration of an object. And I'm not even joking when I say this is super important. This is arguably the most important equation in physics. If you do not learn anything this year, except for this equation, that's not really okay. But if you only learn one thing this year, it needs to be this law, Newton's second law. So just a note, both force and acceleration are vector quantities. We know that already. Both of them have magnitude, but they also have to have direction. And the direction of the net force acting on an object is very important. And we denote that these are vector quantities with these little arrows above the symbols. So anytime you see an arrow above a symbol like that, it means it's a vector and it has magnitude and direction. So let's go ahead and use Newton's second law in an example. So what would be the acceleration on a car with a mass of 2,000 kilograms if the engine is capable of producing a net forward force of 6,000 newtons? So the first thing we're going to do is write down our equation. We have the sum of the forces is equal to the mass of the object times its acceleration. But how are we going to know what the sum of the forces are? Well, draw a free body diagram. So if this is our car right here, what forces are acting on it? Well, we can assume the car is on some kind of planet, probably Earth. So we're going to have the force of gravity pulling it down toward the center of the Earth. But it's not plummeting toward the center of the Earth. Something is keeping it from being pulled down by gravity. Most likely, that is the force of the Earth, the road, the driveway, wherever it is, pushing back up on it. And we have a third force, right? The engine produces a net forward force of 6,000 newtons. So that means there's a force of 6,000 newtons pushing this way. And this is the force of the engine. So we can go ahead and make some assumptions here. Remember, we can add these forces together and we can add these forces together, but we cannot add up and down forces to side forces. It doesn't work that way. So our up and down forces, it turns out, are equal to each other. And when these are equal to each other, we put little tick marks. So one tick mark on the force of the Earth up here is equal to the force of gravity down here. And we know that from Newton's second law. Newton's second law tells us when there is a force, a net external force on an object, it will accelerate. This car is not accelerating up and down, right? It's not jumping off the road and it's not plummeting to the center of the Earth. So we have to assume that there is no net external force in the y direction, the up and down. And in order for there to be no net external force, these need to cancel. So what are we left with net external forces? The only one we're left with is the force of the engine. So we can put that into our equation over here. So the net external force is the force of the engine, which is 6,000 newtons. And that has to be equal to the mass of the car, which is 2,000 kilograms, times the acceleration of the car. And for this problem, we are trying to find the acceleration of the car. What would be the acceleration? So to solve this problem, you want to get A all by itself. So you divide both sides by 2,000. It cancels on this side, and you're left with 6,000 divided by 2,000. Hopefully all of you can do that in your head. And it's 3 on this side, and all we're left with over here is A. So the acceleration of this car is equal to 3. But 3 what? 3 puppies? No. We need units for acceleration here. And hopefully all of you remember that the units for acceleration are meters per second squared. In the first video about forces, I told you that 1 Newton, which is what we measure force in, is equal to a kilogram times a meter per second squared. Hopefully now this makes a little more sense to you, because we measure force in newtons. This is equal to mass, which is measured in kilograms, times acceleration, which is measured in meters per second squared. So the units match the equation. Force equals mass times acceleration, so 1 Newton has to be equal to a kilogram times a meter per second squared. Before we move on to Newton's third law, third and final, these are your homework questions for tonight. So answer the following questions. If a hockey puck with a mass of 0.7 kilograms is pushed with a force of 12 newtons, what is the puck's acceleration if we assume the ice is frictionless? 2. Draw a free body diagram of a person sitting in a chair. What keeps the person from being pulled toward the earth by gravity? If the person has a mass of 65 kilograms, what is their weight? And with what force does the chair need to resist the person's weight? So make sure you answer these questions after you're done watching the entire video, and turn in your answers in the next class. So we already talked about Newton's first law, which is the law of inertia, and Newton's second law, and we summarized that as F equals ma. We have one more left, Newton's third law. So anytime a force is exerted on an object, that force is caused by another object. So if a hand pushes on a desk, that desk ends up pushing back on the hand. That's why if you hit the table, you feel it in your hand. It's not that you're slapping the table, it's that the table is slapping you. Anytime you exert a force on an object, that object exerts a force back on you. It's also true of the skater pushing against the wall over here. The skater wants to push off and move into the center of the rink. So she's going to push out against the wall. But in order for her to actually move backwards, she needs a force acting on her. And the force acting on her is the force of the wall pushing back on her when she pushes against the wall. So the third law says when one object exerts a force on a second object, the second object exerts a force on the first object equal in magnitude to the first, but applied in the opposite direction. That's pretty complicated, so let's summarize it a little bit. More commonly stated, for every action there is an equal and opposite reaction. Even more simple, forces come in pairs. The really important part about this is that these forces are acting on different objects. They are not acting on the same object. Forces are exerted on different objects. This is going to be a sticking point for a lot of you. So make sure you don't try and use them as if these two equal and opposite forces are acting on the same object. If we draw a force diagram for the skater right here, and a force diagram for the wall, let's ignore everything except the arrows that are drawn in the picture here. This one and this one. So the skater is pushing against the wall. So the force that the wall feels is the push by the skater in this direction. And the equal and opposite force here isn't the wall pushing this way. Well, it is, but it's not acting on the wall. It is the wall acting on the skater. So this is the force of the push by the wall. So we have two forces They're opposite in direction, and they are equal in magnitude. But the key point is they work on different objects. They do not work on the same object. This is how rockets work. Rocket propulsion can be explained using Newton's third law. Hot gases from combustion inside the engine spew out of the tail of the rocket at high speeds. And the reaction force is what propels the rocket. The rocket doesn't actually have to push against anything. And this is why a rocket will work in outer space. In space, there's nothing for these gases to push against. Space is pretty much what we call a vacuum, which means there are no molecules of any kind floating around out there. But if you put a rocket in outer space and you turn its thrusters on, it's still going to move forward. And that's because the gases are really hot and they're shooting out of the bottom of the rocket. And in turn, the rocket will move forward. And this is Newton's third law. So go back to the middle of the video about-ish and take a look at the questions and try and answer them the best you can.